Hello, welcome back to our course, Advanced Quantum Mechanics. This is lecture 34. Let me remind you that we still have some unfinished business from earlier in this course. Namely, remember, we studied the Heisenberg picture first. Heisenberg picture, and we looked at the Schrödinger picture. And we also looked at the Dirac picture and the Feynman picture. Dirac picture and the Feynman picture. Now the Feynman picture, I just mentioned really that it has to do with the Green's function and that it's a big deal, but we really didn't do much about the Feynman picture. Let's do this now. So how do these pictures differ from each other? Remember that when we want to calculate an observable, when we want to calculate a prediction for an observable, f bar of t, then this is always this expression, u hat dagger of t, and then f hat, and then u hat of t, and oh, this bar is too much, and psi. The pictures differ in how they bracket. Remember that in the Schrödinger picture, we would bracket this. So we would put a bracket here and a bracket there. And then we would call this the time-dependent state. And of course, you remember that instead, the Heisenberg picture brackets differently. In the Heisenberg picture, we would bracket like this. And then we would say that we have a time-dependent observable. For the Dirac picture, it's a bit more complicated, a bit of both, but overall, it's always about the bracketing. So how does the Feynman picture bracket? Well, the Feynman picture is no bracketing. You see, if we bracket, for example, this way, and then we have psi of t, then we never solve for the time evolution operator, we solve for the time-dependent state directly. If we use the Heisenberg picture, then too, we don't calculate the time evolution operator, we calculate the time evolution of each one of the observables. The Feynman picture says, no, none of this. Instead, in the Feynman picture, we calculate the u hat of t itself. So Feynman calculate u hat of t. Obviously, once you have u hat of t, you can predict the evolution of everything. You can calculate, once you have u hat of t, you can immediately write down what the time-evolved Schrödinger vectors are, or you can also write down what the time-evolved Heisenberg observables are. So the Feynman picture is definitely equivalent. Now, what does it entail? Well, if we use the Schrödinger picture, we have to solve the Schrödinger equation. If we use the Heisenberg picture, we have to solve the Heisenberg equation of motion for the observables. In the Feynman picture, we have to calculate the time evolution operator by solving its differential equation, namely, normally, we solve for this purpose, in order to get u hat of t, we solve IH bar d by dt u hat of t equal to Schrödinger Hamiltonian of t u hat of t. And the initial condition is that u hat of t naught is equal to the identity operator. Okay. That's one way of doing it. Often it is more practical to do this in the position basis. in the position basis, we have that the time evolution operator has matrix elements to the left and to the right. Now we're looking at the matrix elements of the time evolution operator by applying position eigenvectors left and right. And then this is a function of the time and of x and x prime. It is called the Green's function. So the time evolution operator, when written in the position representation, is the Green's function of our theory. And then the normal way to solve for the Green's function is this. Obtain G by solving the above equations here for u in the position representation, which is to say, solving IH bar by dt of G of x and x prime and t equal to Schrödinger Hamiltonian, the position operators in the shorthand notation acting on position functions, and the momentum operators in the shorthand notation. Remember that this p hat is minus IH bar d by dx, and time acting on G of x, x prime of t. And the initial condition, G of x and x prime and t is equal to delta of x minus x prime when the t is 0 at the initial time. This is just translated into the position representation, what we had up here for the time evolution operator. All of this you are familiar with. So it looks pretty conventional. Why then is the Feynman picture such a big deal? It is a big deal because Feynman found another way to calculate the Green's function. So Feynman found another way to calculate G of x, x prime, and t, and it doesn't involve solving any differential equations. See, here we are solving differential equations, not with Feynman's method. No differential equations to solve. Instead, we need to do the path integral. As we will see, this is more than just a technical trick. This is deep. This is more than a technical trick. For one, what we will see is that quantum theory can be derived in a way that is fresh from start. So instead of how we did it in this course, namely by lifting quantum mechanics, classical mechanics from the Newton description to the Hamiltonian description, and then the Hamiltonian description, we were able to generalize to quantum theory. Instead of that, we can also lift Newton's description of classical mechanics to the Lagrangian formulation. And then the Lagrangian formulation can be generalized to obtain quantum theory. But when we do so, we obtain Feynman's version of quantum theory. So that is one thing. We obtain that there is a new Lagrangian basis for quantum theory. And secondly, this is not just a technical trick, as I said, but there's a deeper insight there. Insight. And we will cover that today. The deeper insight is that quantum theory can be viewed as a generalized probability theory which applies in all situations, which applies in those situations when a system evolves undisturbed. Undisturbed and therefore unobserved. Evolves undisturbed and therefore unobserved. Let us start with this deeper insight. In what sense does Feynman derive that quantum theory is a generalized probability theory that applies when systems evolve undisturbed? To see how this comes about, let us start with ordinary probability theory. Recall the ordinary rules of probabilities. There are two basic rules of probabilities that you've always known and always used, even if you haven't seen them axiomatized. The first rule of probabilities is the rule of alternatives. So let's say, e.g., either A1 or A2 happens or something else happens. So it's either or. You can't have that A1 and A2 happen both, right? So it's either one or the other. Then, for exclusive alternatives, we have that the probability for A1 to happen or A2 to happen is equal to, well, the probability that A1 happens plus the probability that A2 happens, right? So it's the probability for A1 to happen plus the probability for A2 to happen. That's the rule of alternatives, of independent alternatives. And then there is a rule of conditionals. This applies in this situation here. assume that an event B can happen if A happened before. In this case, the rule says then the probability for A and B is the probability for A to happen times the probability that B happens if A happened. So B is conditional on A having happened, but B doesn't necessarily happen just because A happened, it's just a possibility, right? So the probability that A and B happen is then the probability that A happens. This makes it possible that B may happen, and it has a certain probability for it. The total probability that A and B both happen is the product of these two probabilities. Now, one might think that these rules are obvious, but they are not. It turns out that for undisturbed systems, for unobserved systems, nature doesn't do this. Nature does something else. Something else that's super similar to this, but crucially different. But first, let's see an example of these ordinary rules of ordinary probability theory in practice. Example. Let's set this example up very carefully. Let's say we have a box. And in this box, we have, let's say, helium gas is in there, filled with helium gas. And now imagine that in this box, we have a tiny little box, and that's our emitter. This will be an emitter. And then we have somewhere else in the box, let's say over here, we have another tiny little thing, and that will be a detector. Now, what do we want to emit and detect here? Let's say it's an emitter of a neon atom. And this is the detector of neon atoms. All this is very hypothetical, of course. Now, why would we use helium and neon? Well, because helium doesn't form molecules and neither does neon, and they don't form molecules with each other. So it's something that makes sense for our purposes. So we have a helium gas in this box, and at some point, let's say at T0, at time T0, one neon atom is emitted at position X emitter, right? So our emitter box is releasing it. That's position XE. And then what happens? Then our neon atom will behave like a soccer ball. It's going to be kicked around by the helium gas, right? So then the neon atom does a random walk, because it is being kicked by the helium atoms. The helium atoms have some temperature, and so they kick around our neon atom. And we let this go for a while, and that means that our neon atom that was emitted over here at XE, we can go on a random walk anywhere in this box. It might go over here, then there, then there, then there, but anywhere it wants. And then our detector here is at position XD. And then let's say at some later time, at some time t, the detector checks if the neon atom is at location XD of the detector. In practice, of course, we can't really localize these particles in a point and measure them at a point. It's always to be thought of as a little volume there, that we localize our neon atom initially, and then a little volume in which we look for the neon atom later on. But we don't want to be bothered with describing exactly the shape and size of that volume and all of that. Let's just simplify things and say it starts at a point and then ends at a point. I will say a little bit more about this later on. It's not a significant constraint, but that we consider the start and end points to be point-like, but it serves us a lot on in notation and simplicity of the formulas. All right, so we release a neon atom into the gas, into the helium gas here at the time t0, and then we look for it over there at time t. Chances are we're not going to find it, right? What are the chances? It could be anywhere in here, but there's a probability that it will be found over there. If we do the experiment many, many times, and of course we always consider an ensemble, then there's a chance that we find it over there. Now, what is that chance? There is some probability, right? And what is that probability? Let's give it a name. So we have, okay, then the probability for detecting the atom there, for detection, obeys simply by the basic rules of probability that we discussed above. It obeys the following rule, namely, the probability for our neon atom to go from this initial place and time to the detection location at time t is equal to the integral over the box of the probability of the neon atom to have traveled at the initial location, at the initial time, then onwards to some intermediary location at an intermediary time t prime, and then from there onwards, that it then traveled from that location and time to the desired location and time. I hope I can move this. Right. dx tilde, d3x tilde. So this is not a method for calculating that probability. For that, we would need to know the gas dynamics, the temperature, and all those things. No, it's just a general probabilistic statement that must be true. Namely that the probability for the particle emitted here and then to arrive here and there at that time is the probability that it traveled to this intermediate location at an immediate time and then onward from that intermediate location at the intermediate time to the target, to the detector, if we sum over all possible intermediate locations that it might have been at the intermediate time. Right? Because it's got to be somewhere. So what we see here is that these are conditionals. We here use the conditional probabilities rule, the conditionals. You see, for it to arrive at the detector from an intermediate position, it had to arrive at the intermediate position first, right? So we have to take the probability that it makes it to the intermediate position x tilde, and then multiplied it with the probability that it goes from that intermediate position to the detector. And here we are integrating over the volume of the box. This is the addition rule for alternatives. Alternatives add, conditionals multiply. And alternatives add, you see, at the time t prime, which is arbitrary, by the way, so we have t naught smaller t prime smaller t, of course. At that intermediate time t prime, our neon atom has to be somewhere. So there are these many alternatives for where it might be then. It might be at any one of those locations x tilde. And so, because they're exclusive alternatives, it's either here or there or there or there or there, we have that these probabilities add up. So we have here in this formula both the addition rule and the multiplication rule, the rule for alternatives and the rule for conditionals, both manifested. All right, so this is how probabilities ordinarily work. There's nothing quantum mechanical about this. That's just ordinary probability theory. Oh, what we should keep in mind here that in this situation here, the helium atoms are keeping an eye on where the neon atom is at all times, because the neon atom gets kicked around by the helium atoms all the time. These helium atoms basically continually measure where our neon atom is at the moment. Even if we don't question the helium atoms, we don't ask them, where did you see the neon atom? Even if we don't know where the neon atom is, the neon atom has interacted with its environment, and its position, therefore, has been localized. The position wave function collapses to locations that are determined by where the helium detected where the neon is. In other words, the neon atom is traveling a random path through the gas, but that path is not a mystery. That path is observed because the neon atom is continually interacting with the helium atoms from the environment. Now, let's look at the quantum mechanical situation. In quantum mechanics, we have that the probability that a particle travels from an initial location xe at time t naught to a location xd at time t, if undisturbed, is equal to g of xd xd E, T, and T naught. That's the Green's function modulus squared, which is the Green's function, remember, is the consists of the matrix elements of the time evolution operator. So u hat of T and T naught xe modulus squared. So this is true for our neon atom if the box is otherwise empty, is empty. No helium, no other particles, for example, no photons, no other particles, only the neon atom. Why? Because then the neon atom evolves freely, undisturbed, just according to Schrödinger equation, or according to the unitary time evolution operators. Undisturbed, undisturbed, unmeasured. Now, so what's the situation now? Now we have again the box of above, and we release a neon atom here, but we do not release it into a gas of helium, but we just release it. Then what will happen? Well, its wave function is going to spread. This is what quantum mechanical wave functions do. And so the neon atom will just spread, and the wave function of the neon atom will just spread in the box. And then if at a later time we perform a measurement and look for the neon atom, then there's a finite probability we might find it. Now, it's not because it has been kicked around by helium atoms until it happens to arrive there. No, now it would be there because the wave function has spread. And that means that there is a finite probability for finding the neon atom over there. Okay, so let's calculate that probability now, and let's check whether that probability obeys this equation in red here. This equation that expresses the probability for emission and then absorption by the detector with an intermediate time. Let's see if that's still true in the case where the box is empty and our neon atom travels alone. So for this, we need to calculate the probabilities in more detail. So this is the probability for the neon atom to travel in an empty box from the emission point to the detection point from time t naught to time t. And I claimed it is the Green's function modulo squared, which is this expression. Maybe it's good if I prove that again. I hope you remember this is the case. I think we covered that when we covered Green's functions, but let's just prove this. So, proof. Well, what is the observable that describes our detector? The observable of the detector is Q hat, which is X detector, X detector. Right? That's the projector onto the position XT. Strictly speaking, we ought to integrate here over a little volume so that it really becomes a projector and so on. But again, it would be unnecessarily tedious, and we can work with this for now. So this is the observable of our detector. It checks whether the particle that we are looking for is at position xd or not. And what we have is that the measurement apparatus that corresponds to q hat has an output which is either 1 or 0s. Apparatus outputs one of the two eigenvalues. Remember, a projector has eigenvalues 1 and 0. Outputs 1 if the neon atom detected, and it outputs 0 if not. So therefore, in an ensemble, so if we run the experiment many, many times, the Q bar is the average number of detections here. It is the probability, therefore. So we have that Q bar is the probability for detection. Well, at xd. This means that the probability that we are interested in is the following. So therefore, the probability for our neon particle to travel from the emission location at time t0 to the detection location at time t is equal to, I need more space, I think. It is equal to x e u hat dagger of t0, and then our observable q hat, and then u hat of t0 xe. Do you see why that is? So this is q bar of t. Why is that true? Well, you see, this is the time-evolved initial state. That's the initial state. This is how we release our neon particle. We know where it is. And then it propagates according to the time evolution operator. That state evolves according to the time evolution operator. Here's the same thing. And then we calculate q bar, which is the probability for the particle to be in the xd state. Now, let's write out what that is explicitly. After all, we do know what q is. It's this projector. So this is xe u hat dagger of t and t0, and then xd, because that's what this operator is, and then u hat of t and t0 xe. Now we recognize what we're dealing with, because this is a Green's function, right? These are just position matrix elements of the time evolution operator. And this is the complex conjugate of that. So therefore, this is equal to xd u hat of t0 xe modulus squared. And since this is a Green's function, we can also write it as modulus squared of g of xd xe t0 modulus squared. This is what we had at the beginning. We said that in quantum mechanics, the probability for a particle like such as a neon atom to propagate if undisturbed from an initial location to a final location in a particular time span is given by the Green's function modulus squared. Green's function being the position matrix elements of the time evolution operator. Okay, so the probability is given by the Green's function modulus squared. Remember, we gave a name to the complex number in here before we take the modulus square of it. Namely, that is what is called the probability amplitude. So what we see here is that here g of xd xe t t naught, which is also xd u hat of t t naught xe is the probability amplitude. And we will write it in the following way. We will write the probability, sorry, we used to write probability, now we write probability amplitude of the particle, such as a neon atom, to start at the emission place at time t naught, and then to travel to the detection place at time t. That probability amplitude is a complex number, and it is, you know, xd u hat of t naught xe, right? So that's the probability amplitude. It's the Green's function. It is g of xe xd t naught. I think I wrote it differently before. Okay, so here's the xd, here's the xd, and here's xe. Okay, so that's the probability amplitude. If we take the modulus square of it, then we obtain the probability. So for now, let's keep stock. Let's summarize. We found that quantum mechanics naturally gives us the ability to calculate the Green's function. It's just the matrix elements of the time evolution operator. And the Green's function isn't giving us the probability directly for the process to happen, for the neon atom to go from here to there. No, it gives us the probability amplitude for it. But then to get the probability is easy. We just take the modulus square of it. All right. Now, let us again consider an intermediate time. Remember, in the case where the box was filled with helium gas, we said, we don't know how to calculate the probability for the neon atom to diffuse by being kicked around by the helium atoms from this location to that location in a particular time interval. But we do know that this probability has to obey a certain condition. If we look at an intermediate time, namely that the probability for traveling from the initial position and time to the final position at the final time is given by the sum over all possibilities where it might be at an intermediate time t prime that we fix somewhere between t naught and t. The probability for it to have traveled to that some intermediate place x tilde, and then onwards from x tilde to the target, and we integrate over all x tildes. They're conditional probabilities, and then we sum them up because they're alternatives. Right. Now let's look at a similar construction, but now for the quantum case. What happens if we take an intermediate time? Choose an intermediate time. So choose a time t naught smaller t prime smaller t again. just like before. Then, what can we tell on general quantum mechanical grounds? Well, we know that the time evolution operator is simply a composition of time evolution operators, right? We evolve the Schrödinger equation from here to there, and then from there to here. The time evolution operator is always compositional. So we always have that this is u hat of t prime times u hat of t prime t naught. For example, for constant h hat, we have, for constant h hat, we have that e to the power of 1 over I h bar t minus t naught h hat, that would be this time evolution operator, is equal to e to the power of 1 over I h bar t minus t prime h hat, that's this time evolution operator, times e to the power of 1 over I h bar t prime minus t naught h hat. That's this time evolution operator. And why is this true? Well, you see, there's only one operator in here. It's h hat, h hat. And h hat commutes with itself. It just behaves like a number in this product of exponentials. Therefore, we can pull these two exponentials together, just like we always can do with numbers. And then we see that the e to the power of 1 over I h bar minus t prime h hat cancels the e to the power I h bar plus t prime h hat, and we're just left with this. All right, but it's of course generally true, even when the Hamiltonian is time dependent, but then you have to work with the time ordering operator, and the time ordering operator will make sure that this is the sequence in which the unitaries have to be written. Okay, so since this is true, as it was just a comment, since this is true, we can conclude that the probability amplitudes that is to say, the Green's functions, obey the following rule. See, the Green's function is xd u hat of t naught xe, right? That's the probability amplitude for the particle to travel from the initial emission place to the final detection place at the times that we choose. So this we can now write as xd and then u hat of the evolution from t prime to t times the evolution from t naught to t prime of xe. Just using that the time evolution operator is factorizing in this way, as it always does in every quantum theory. So here we now insert a resolution of the identity in terms of the position eigenvectors. Then we find that this is equal to, let's use some more space, integral over the box of xd and then u hat t prime. I'm just carrying forward what we had here, right? And then we insert the resolution of the identity, namely x tilde, that's the resolution of the identity together with the integral here. This is an integral over all x tilde in R3, confined to the box because the particle is not supposed to be able to come out of the box. And then u hat of t prime, t naught, I'm just carrying forward what we had over here, and then we have here d3 x tilde. Now, you see, this is a probability amplitude, and that is the probability amplitude, right? This is the probability amplitude for the particle to travel from the emission point at time t naught to the intermediate point x tilde at the intermediate time t prime. Actually, I can put the state vector in here. And similarly, this is a probability amplitude, not the probability, because it's not modulus squared, probability amplitude for the particle to travel from x tilde at time x t prime to xd at time t. And this, of course, is the probability for the particle to travel from xe at time t naught to xd at time t. Okay, let me write that equation nicely again. And since this takes a little while, I will just magically do this. You see how quickly this can go with magic? So we have here that the probability, sorry, made a mistake, wasn't so magical after all. The probability amplitude for the particle to travel from the emission location to some intermediate, to the detector location at the final time is equal to the sum over all intermediate locations x tilde, or the integral over all intermediate locations at x tilde at some arbitrary time t naught smaller t tilde smaller t, at some arbitrary intermediate time t tilde, the sum over all possibilities where it travels from the initial emission to the intermediate point at the intermediate time, multiplied with the probability amplitude that it went from the intermediate position at the intermediate time to the detector location at time t. This equation needs to be compared with the equation that we had for the case where the box was filled with helium. What did we have there? Here, this is what we had. So when the box was filled with helium gas, then the probability for the neon atom to make it from the emission location to the detector location at the right time was also the integral of the box. Also probabilities here to travel from the emission point to the intermediate point, from the intermediate point to the final point, but with the helium, we had probabilities here. Without the helium, without observations, without interactions, when the neon is undisturbed, then we have probability amplitudes here. So what we have here is an astounding conclusion, which is that when a system such as a neon atom, but the same argument can be made about whatever system, when a system such as a neon atom is undisturbed, is evolving undisturbed, i.e. unmeasured or unobserved, then its probability amplitudes, obey the usual addition and multiplication rules for alternatives and conditionals. Right? Because it's the same structure here, that it makes it to the intermediate point, and then from the intermediate point to the detector. That's a conditional probability. And we see here, you have to multiply the probability amplitudes to get that. And then there are many different alternative locations where the neon atom could be at the intermediate time, namely anywhere in the box. And these probabilities add up. Actually, it's probabilities and probability amplitudes that now add up in the form of this integral, because it's a continuum of locations. We are not adding, we are integrating. Okay, so this is crucial. This is the deep insight that I was telling you about, namely that when a system evolves in an undisturbed way, if it doesn't interact with another system, then its probability amplitudes obey the rules of probability. But this also means that its probabilities do not obey the rules of probability. Right? So the moduli squared do not obey the usual additional multiplication rules then. So notice, in this case, that is to say, in the unobserved case, in this case, the probabilities do not obey these rules. In other words, whether you first take probability amplitudes and add them for alternatives, and then take the modulus squared, is not the same as if you took two probability amplitudes, took their modulus squared, and then add them, right? Because for complex numbers, because for C1, C2 in C, we have that C1 plus C2 modulus squared is generally not the same as C1 modulus squared plus C2 modulus squared. Therefore, this equation here does not imply the equation above. It just doesn't, right? It doesn't imply this equation here, because here this summation doesn't commute with this squaring here, right? Over here we would have the here we have these probability amplitudes, and you can't just put a square on the modulus square on this, modulus square on that, and then expect that this would be the modulus square over there. It's of course not, because here you have a sum or an integral, and then you run into this problem. Okay, so the deep insight here is that the difference between classical mechanics and quantum mechanics can be viewed as a difference in probability theory. As long as things are behaving quantum mechanically, which is to say undisturbed, according to just unitary time evolution, the probability rules are obeyed, but by the probability amplitudes, and not the probabilities. And then, as soon as you observe things, the observed things will, of course, obey the ordinary rules of probability. Now, at this point, you may wonder, good, fine, but why is this useful? Here's how this becomes useful. Let us introduce more intermediate times. use more intermediate times. So T0 smaller T1, smaller T2, smaller T3, smaller ... smaller Tn, smaller T. Lots of intermediate times introduced. And then we can do what we did before. We can write now the time evolution operator from T0 to T as the product of time evolution operators from T0 to T1 times the time evolution operator from T1 to T2 times the time evolution operator from T2 to T3, etc., until we have the time evolution operator from Tn to T. And so we have this huge product of time evolution operators. And then we can insert between any two of them a resolution of the identity, just as we did here. Insert a resolution of the identity in the position basis. So now we get not just one integral, we get many integrals, namely capital N integrals if we insert capital N resolutions of the identity, because we split the time evolution operator into n time evolutions. And when we do that, what do we get? We get a formula just like this one, but way longer. Namely, now what we will get is that the probability amplitude for the neon atom to travel from the initial point to the final point in the detector is given by multiple integrals, and then in here probability amplitudes times probability amplitudes times probability amplitudes, namely probability amplitude to travel from initial location to location x1, and then from x1 to x2, and then from x2 to x3, etc., at the various times. So that becomes initially a rather complicated formula then, but here's how it looks like, and I will show you in a moment what it is and why it's useful. So then we obtain that our Green's function from the emission location to the detection location is given by, well, the probability amplitude, of course, of x e at t0 into x detector at t. And this now is an integral, integrals. How many? N of them, because we have n intermediate times. And then it's the probability amplitude of the particle traveling from, that's not a P, traveling from the emission location at time t0 to intermediate location x1 at time t1 times the probability amplitude for it to travel from x1 at intermediate time t1 to location x2, intermediate location x2 at time t2 times, and you see how this is going, probably amplitude, and then etc. ... traveling from intermediate location to intermediate location, where all the intermediate locations are possible here, right? Because we are integrating over x1, integrating over x2, etc. And eventually we have here the probability amplitude for the particle to travel from xn, this intermediate location, at time tn, all the way to our detector at time t. And d3, this is over the box, of course, every time, d3 x1, d3 x2, d3 x3, ... d3 xn. Well, why would we want to do this? This is a really lengthy formula. And the larger we choose n, the more terms we have in this huge product, right? We multiply this probability amplitude with that probability amplitude, with that probability amplitude. It's just a huge product of conditionals, right? Where we have, well, if it travels from here to this intermediate point, then it might travel from there to that intermediate point, etc. Now, what is this therefore? Well, you see, this is basically of the form sum over, or integral over, the probability amplitude. If I just combine these things now, right? So here we have the probability amplitude for the particle to make its way from xe to x1. And here's the probability amplitude for it to go from x1 to x2, and so on. So therefore, this is really the probability amplitude. Sorry, I need more integrals here, right? So boop, 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 all those integrals, n of them. And then it's the probability amplitude for the particle to travel. Let me just symbolically write it in this way. To travel from xe to x1 to x2 to to xn, and from xn to x detector at the intermediate times. Let's just not bother writing out the intermediate times. They are understood to be fixed there. And then d3x1, d3x2, d3x3 dot 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 d3xn. You see what this is doing is, this is the probability amplitude for our neon atom to take a path, namely to go from xe to x1 to x2 to xn to xt. So therefore, we can write this as the integral in a symbolic way. We can write this as the path integral over all paths. And the integrand is the probability amplitude for a path from xe at t naught to xd at t. And then we can write that integrand as dx of t. This is just a symbolic notation here. All right, so you might think, okay, this is the Feynman path integral, right? So let me just write out again what this is. This is g of xd, xe, t, comma, t naught. This is the holy grail of quantum mechanics, the Green's function, because the Green's function is the time evolution operator at a particular time, in a particular basis, in the position basis, right? So if we have the Green's function, we know everything about the quantum theory. And here we have a way to express the Green's function as an integral, where we're not integrating over numbers, we're integrating over paths. If you spell it out, it's this infinite product of integrals. Infinite, why? Well, of course, from here to here, we let n go to infinity so that we can obtain smooth paths, right? Not jumps from xe to x1 to x2 to x3, etc., but so that it's, the time evolutions are shorter and shorter. So we have a sum or an integral over probability amplitudes for each path. Each path has a probability amplitude, and we have to sum up the probability amplitudes for all paths. Now this is easier said than done. Obviously, we have infinitely many integrals to do here. And notice that there is in this derivation nothing that forces our paths to become smooth. If n goes to infinity, we will include smooth paths. But most paths are not smooth, are jumps, right? Because the x1, the x2, the x3 are independent of each other. So actually, to define this so-called Feynman path integral is analytically very hard. This is the Feynman path integral, right? And it's mathematically, analytically very hard to even define this properly, to take that limit in a way that makes sense. So you may think now at this point that this is sort of a small victory here, because yes, we have achieved what we set out to do, namely to calculate the Green's function in a novel way. The old-fashioned way is to solve its differential equations. You know, it's just IH bar d by dt of the Green's function is equal to Schrödinger Hamiltonian acting on the Green's function. We don't need to calculate it this way anymore. No, instead, we can calculate this extremely complicated path integral here. So you might think, yeah, it's a small victory. We can do an alternative to solving a differential equation. We can solve the path integral. But how difficult is that going to be? Now, here's the deal. In practice, in applications of quantum theory to quantum field theory, for particle physics, for example, the path integral is way more convenient than is the ordinary method of solving differential equations. And why is that? Well, the reason for that is that we never do the integral this way. And it's the same as we ordinarily integrate. I'm sure it hasn't been a long time since you last integrated some function. Now, when you did that, when you integrated the function most recently, did you calculate it using the Riemann limit? Did you write down the integral as a sum over a partitioning of the x-axis into small intervals and then calculated the rectangles and then summed up the areas of the rectangles and then took the limit for the widths of the intervals to go to 0 so that you get infinitely many of those rectangles? Probably not. Probably you didn't bother calculating the integral this way. Instead, you used tricks. You used probably something like integration by parts, or the substitution rule, or contra-integration. It's similar with the path integral. The path integral is super tedious, way more tedious than the Riemann integral if you want to make sense of it. I mean, the Riemann integral at least is well defined, but the path integral is not properly defined analytically. But fortunately, we don't actually have to do it this way. We can use tricks similar or analogous to integration by parts and the substitution rule also for the path integral. And that suddenly makes the path integral a very powerful method. So powerful that it is the method of choice in studies of quantum field theory. Not so much in quantum information yet, but in quantum field theory and particle physics, it's the method of choice. All right, so this is as far as we get today. We will continue on Friday. See you then. Bye-bye.